Continuing into our thermochemistry, we're going to take a look at latent heat. Now, latent heat is very similar to specific heat since it deals with heat energy and a substance. Specific heat was the amount of energy required to change the temperature of a substance. Latent heat is going to be the energy required to change the state of matter of a substance. So latent heat is energy required to change the state of matter of a substance. Some substances require a lot of energy to change its state of matter. State of matter being liquid, solid, and gas. Whereas other substances don't take near as much energy. If you've ever put rubbing alcohol on your arm, it doesn't take much to evaporate it. It doesn't take much energy. Or if you've ever tried to melt metal, it takes a whole lot of energy to melt something like iron. So a substance has a specific amount of energy that it needs to change that state of matter, whether it be liquid, solid, or gas, but all substances have different latent heats, very similar to all substances having different specific heats. So there's going to be two types of latent heat we're going to talk about. There's fusion and there is vaporization. The difference between these two terms is which state of matter we're talking about. Fusion deals with solids changing to liquids and vice versa, so liquids also changing back to solids. Vaporization deals with liquids changing to gas, and once again vice versa, gas changing back to liquids. Typically, latent heat of vaporization is much higher than the latent heat of fusion for each substance. For example, water. The latent heat of fusion for water is 334 joules per gram. So if you want to take an ice cube and melt it, it's going to take 334 joules for every gram of that ice cube that you have. Or if you have some water you want to boil, the latent heat of vaporization for water is around 2,260 joules per gram, which means if you want to boil some water, it's going to require 2,260 joules for every gram of that water that you have. So one important thing to keep in mind when you're working out latent heat is what your temperature is. So if you got water at 100 degrees, you're going to be dealing with liquid and gas. It's not going to be a solid at that temperature because the melting point and freezing point of water is 0 degrees Celsius. So you really got to pay attention to those temperatures. And to help you do that, there's plenty of resources and charts available online, or your teacher may even give you some. So this particular chart, it has a couple of substances listed out. It tells you your specific latent heat of fusion. And take note to the unit that it's in. It's in kilojoules per kilogram. Kilojoules per kilogram is the same as joules per gram. So water, for example, its latent heat of fusion is 334 kilojoules per kilogram, which is the same as saying it's 334 joules per gram. Its latent heat of vaporization, 2,258 more specifically than I said earlier. And that's going to be when water is at 100. The latent heat of fusion is going to be when the water is at 0 degrees. So the temperature truly plays a difference. So since it's joules per gram, that also kind of gives you a hint at what your formula is for latent heat. So our latent heat formula is Q equals mL. Q, as it was earlier, is energy, heat energy to be precise, and it is measured in joules can also be measured in kilojoules. M is going to be mass. That will be measured in grams, can also be measured in kilograms. And L is your latent heat constant. Now, as we said earlier, there's two latent heats, though, you got to pay attention to. There's fusion and vaporization. Latent heat of fusion, latent heat of vaporization. You'll have to choose which constant you use based on the temperature it's at and what state of matter you're dealing with. So if you're dealing with a solid, choose fusion. If you're dealing with a gas, choose vaporization. Liquids account for both of those constants. So either going from a solid to a liquid, or a liquid to a solid, or gas to a liquid, and liquid to a gas. So the key difference between those two is fusion is solid, vaporization is gas. But do take note, this formula does not mention anything about temperature. So your temperature during a phase change, or when it's melting, or boiling, condensing, or just changing its state of matter, will stay the same momentarily. And we'll get to why in the next lesson. So for now, let's just try a couple practice problems and see what we can figure out with this concept. So our first question says, how much heat is given off when 2 kilograms of water freezes? Assume the temperature stays constant at 0 degrees Celsius. It's very important our temperature stays constant, because if we change the temperature, we're moving into specific heat, and we'd have to add that to our calculations. So we want our temperature to stay constant for the time being. All right, since we're doing latent heat, we're going to need Q, M, L. Let's just pick out our units here. So it says how much heat is given off. That means I'm looking for that heat energy. I'm looking for Q. When 2 kilograms of water freezes. So my mass is 2 kilograms. Well, what's my latent heat? Since I'm dealing with freezing, freezing means solids. I need to know what's the latent heat of fusion. So I go to my chart. Latent heat of fusion for water, 334 kilojoules per kilogram, which is the same as joules per gram. So this is going to be 334 kilojoules per kilogram. Now we can set up our formula. Our formula is Q equals ML. Very simple formula. So Q is what I'm looking for. That's going to be X equals my mass, which is 2 kilograms, times my latent heat, which is 334. Now it's very important you make sure these units are consistent. So I got kilograms and kilograms. So my energy will be in kilojoules when I solve for it. So X equals 2 times 334, so I'm going to get 668. And my unit we just said, since it's energy, is kilojoules, since my latent heat was in kilojoules. And there is our answer. Let's look at another one. How much heat must be added to a 25-gram ice cube at 0 degrees to change it to water at 0 degrees? So once again, our temperature is not changing. That's very important for right now. We have an ice cube, which means a solid. We got 25 grams. So I'm doing latent heat, so I need Q, ml. I'm looking for how much heat. So that means I'm looking for this Q. My mass is 25 grams. My latent heat is what we got to look up. So you go to your reference chart. I'm dealing with water. Fusion of water, since it's a solid, it's 334 kilojoules per kilogram. We said kilojoules per kilogram is the same as joules per gram. So this time it's going to be 334 joules per gram. So I set up my formula. Q equals ml. Q is X, that's what I'm looking for. The mass is 25. Latent heat is 334. Solve for X, all we got to do is multiply 25 times 334. We get 8,350. And since my latent heat was in joules per gram, this will be joules. And there is our answer. Let's do another one. Let's calculate the energy transferred. So I know I'm using QML. When 15 grams of water vapor condenses, that means I'm dealing with a gas. My mass is 15 grams. And it condenses on a bottle at 100 degrees Celsius. It also asks, is energy absorbed or released? So we're looking for Q. I need to know that vaporization constant. So I go to my chart. Latent heat of vaporization is 2258. I'm going to round it to 2260. And that is joules per gram. So set up my formula. Q equals ml. I'm looking for Q, that's X. Mass is 15. Latent heat of vaporization is 2260. So to solve for X, we just multiply 15 times 2260. X equals 33,900 joules. You could also do 33.9 kilojoules. Either way, but there is our answer. And as you can see, the vaporization of water is much higher than the fusion of water. And then the last question asks, is energy absorbed or released? When you condense, you cool down. When you cool down, you release energy. So this is going to be released. Now, if you released energy, it's indicated by a negative. So that means our latent heat here needed to be negative. That makes this value negative. That makes this answer negative. Make sure you always pay attention to the way things are written. Because if it's condensing, it's cooling down. It needs to be a negative value for your Q. If that negative wasn't there, it would be inaccurate. For your answer, it would be wrong. Even though numerically it's correct. Alright, let's do another one. How much energy is transferred when 50 grams of liquid hydrogen changes to a gas at negative 253 degrees Celsius? Is energy absorbed or released? So I got Q, M, and L. I'm looking for Q. My mass is 50. And this time I'm dealing with hydrogen, liquid hydrogen. So I need to look up my latent heat. But which one do I need? Do I need fusion or vaporization? Well, it says we're changing to a gas. So I need to know vaporization. So I go to hydrogen. The vaporization of hydrogen is 449. So I got 449. Now is it negative or is it positive? We're going from a liquid to a gas. That means it's heating up, so it should be positive. And this will be joules per gram. So we set up our formula. Q equals ml. Q is X. Mass is 50. Latent heat of vaporization is 449. Solve for X. All we got to do is multiply 50 by 449. So our answer is 22,454 joules. You could also say 22.5 rounded kilojoules for your answer. And as we said, heat was absorbed. Since it heated up, that makes that value positive. And let's do one last one. How much heat must be released to change 100 grams oxygen gas into a liquid? So let's set up our variables. We're looking for heat. Our mass is 100 grams. Our latent heat. Now, what state of matter are we dealing with? Well, we're going from a gas into a liquid. That means it's cooling down. So whatever this value is needs to be negative. Let's check our chart for oxygen, vaporization of oxygen. So the vaporization of oxygen is 213. But in this case, it's negative 213 joules per gram. So our formula is Q equals mL. Q is X. Mass is 100. Latent heat of vaporization is 213. So 100 times 213. You got 21,300 joules. Could also do 21.3 kilojoules for your answer as well. All right. So that is latent heat. It's the amount of energy required to change the state of matter of a substance. It's fairly simple to calculate. There's only 3 variables. Make sure your units are consistent between your mass and your latent heat constant and your energy in some cases. Make sure you choose the correct latent heat constant. So if you're going to use fusion, you'll see words like melting and freezing. Vaporization goes for condensation and boiling. It deals with gases. So make sure you pay close attention to the state of matter that it is changing to and from. And I hope this video helps. And as always, good luck on your tests.